Okay, so last time we talked about ways of assigning tags to the sentence elements, part of speech tagging, and we talked about using Markov models, hidden Markov models for that, and that was the idea. Let's go back and let's try to remember. Okay. So the formulation started from here. Okay. We said that that's what we are going to do. Given these words in a sentence, or in a not necessarily in a sentence, but giving the words numbered from 1 to n, we like to assign these tags for each word, and we like to build a model, a statistical model, that will measure the probability of assigning these tags to the words, and we like to keep this maximal. And as always, doing this directly is not that easy. It is not operational. Let's use the bias rule to write it the other way. So it will be the same as, this is not an approximation, it is the same as, okay, assigning a probability to the tags, and then giving the tags the probability of those words. And then we say that let's do some approximations now, okay, after this. So what we are doing is this approximation of Markov, and we are saying that a tag depends only on the previous tag, ignoring the others, and that's one approximation. These are the transition probabilities. The other one is my observation is only dependent on the current observation, not the previous observations. Okay, so we divided our problem into two, coming up with the prior probability and the likelihood probability, and we simplified each of them with these two assumptions. And at the end, I get these two things. So that's where the hidden Markov model comes in. Hidden Markov model says that, okay, if you calculate these transition probabilities and if you calculate these observation probabilities, you're going to give me a very good approximation for the original problem. That's what we did, and we talked about it, and then we talked about the examples, and we moved on. We solved this problem, I guess. I mean, the Secretariat is expected to raise tomorrow, and Secretariat is expected to raise tomorrow again. Is this raise a noun raise or the verb raise? We talked about that by multiplying the transition probabilities and the observation probabilities, and we saw that raise has to be here a verb, because there is a very strong evidence after it is coming from to. Okay, we looked at this example. What else? So then we talked about the Markov chain, observable Markov models. Everything happening inside that Markov chain is we are observing it. That was one classical example. First order Markov chain, and it is observable. There is nothing hidden in it. What we are going to do is, but is hidden. In that case, we will say that we have our states, and I guess that was the thing that, yeah, this was the place that we stopped, maybe, or maybe just after this point. I don't remember exactly, but let's start talking about this at this point. Okay, so for the hidden Markov model, we should have these 5 elements: 1, 2, 3, 4, 5 states. How many states do I have? Okay, so states are actually our hidden states. We don't know what state I will be in. I only have observations for each state. Okay, so depending on the number of words you have in your sentence, let's say I have n words, so we will have n different states for each word, and our observations will be our words, but we don't know what the states are. So our task will be to guess what the states are depending on the observations. We have the transition probabilities. If my previous state is noun, okay, what is the probability that I will have a verb after that? Okay, so that's the transition probability. These are the observation likelihood. It says that, okay, if I am observing a word race, what is the probability that I am going to assign a verb to this word race, etc. And for the initial probabilities, from what state should I start? Those are the probabilities, because for the first element of the sentence we don't have the transition. So those 5 things will make a hidden Markov model. And you remember this silly example. You remember the example? Says that if I like to know how hot last year's summer was, so I don't remember how hot the days were, but I recorded somehow how many bars of ice cream I ate. So for one day I ate 1, then 2, then 3, 2, 2. So by looking at this observations only, can I guess how hot the days were? What is the maximum possible answer for this? Of course, I will never know what the exact days were in terms of their hotness or coldness, but this will be a sequence of assignments that will make this observation maximum, like with that observation maximum. So we talked about those, okay, and we said that why don't we apply the same idea to the words, okay. So these are my transition probabilities between the states. But in real life, nobody will give you the states. I mean, these should be hidden, so I have my observation stuff, and that's where the observation stuff comes from. Okay, so these will give me the transition probabilities. A02, A01, and A03. I don't have 04, right? So I don't have 04, yeah. So these are the, remember that special probabilities pi. Okay. So the sum of these 3 should add up to 1.0. This one will tell you what is the probability that a sentence should start with a 2. Okay. This one will tell you what is the probability that the sentence will start a verb. And this one will tell you probability that the sentence will start with a noun. Okay, 3 things here. And this one will tell you the probability that after 2 the sentence is going to end. This one will tell you the probability of having another 2 after 2, etc. So these are the transition probabilities. We measure them, we do them with a matrix like this. And this is A00, this is A10, this is A20. So how many lines do I have? What is the number of lines?
4.
What? 4?
4.
4. I'm not asking for this exam. I am asking it for general. What is the number of lines? How many lines?
Number of states.
Number of?
States.
Number of states, it is the number of tags, right?
Yeah.
Plus 2. Okay. This and this. Start and end. So the number of lines and number of columns are the number of tags plus 2. And is this a symmetric matrix or not? Is
No, not no.
Yeah. Is 1 0 same as is 0 1? No, it is not. Right? Because
A verb can come after 2, but a 2
Yeah.
cannot come after verb.
yeah, both of them are possible, but one of them is very, very small value. Okay, so these are the transition probabilities, and then we have the likelihood, observation likelihoods. Okay. Out of all the places that you have seen a verb, how many times did it turn out to be an awkward? It's kind of a. So this is another mammal. who I was talking to somebody. Are we talking about mammals? This is a mammal.
Okay.
We were talking about the mammals last time.
Last time,
Yeah, so it's a mammal. So it's a member with since it starts with two A's, usually at the beginning of the dictionaries you have seen this animal. Okay. So that's the meaning of it. The observation probabilities these are. Okay. So I calculate this. How do I calculate it? I calculate it from my marked data set. Again, how do I calculate these? I calculate them from marked data set. So I have my observation likelihoods. I have my transition probabilities. The rest of so I know how to divide this into two: the transition probabilities times the observation likelihoods. Okay, and I know that one. So my task is going to be, if my sentence, if my n is 10, if I have 10 words in a sentence, okay, if I have 10 words in a sentence, those words are fixed. I need to come up with 10 tags for these words, okay, and measure this probability. I know how to measure this probability now, and find the tag set that makes this probability maximum. It should be as close to 1 as possible. Okay, so every time I make a new assignment to one of these words is, let's say I am using a 45 tag set, 45 tag set. Okay, so and suppose I have 7 words in my sentence. It is 45 to the 7. It's a very large number. I don't like these kind of large numbers. I can't deal with this. Maybe for small values of n, but for values like 10, 15, 100, it's not going to work. So we need to come up with a better way of doing this. Okay, so we are going to use this actually. We are going to use this idea of dynamic programming again, and this will be our 3rd time we are using dynamic programming, 5th time, I don't remember. I mean, that was my promise at the beginning of the semester, right? We were going to use dynamic programming a lot, and we are going to use dynamic programming today too. And for the next chapter, parsing chapter, we are going to use the dynamic programming again. Okay, so let's visit this dynamic programming idea again. Before doing that, let me make our previous assumption. Remember our approximations? I made them a little bit. Okay. So instead of making this assumption, if I make this assumption, pi I is from 1 to n p t I. What does that mean? It means that a tag doesn't depend on anything. It just takes the tag. It can happen anywhere, and its probability is the tag of the probability tag. If I do this, what would be my complexity of assigning? What would be my complexity of assigning probabilities to a given sentence?
N.
It should be as simple as what? 45 times n, right?
Yes.
That would be that simple, okay? But I am dependent on the previous tag, okay? I am not dependent on all the tags that come before me, but I am dependent on the previous tag. So if I consider all the previous tags and my tags, so 45 times 45 should be enough to make a decision about all the tags that I have inspected so far. So the idea is kind of like that. That's what we are going to do. Let me go there again.
Can you repeat that again? I didn't catch that.
So this one says that assuming all the tags depend on each other,
Okay.
when I change one tag, okay, when I change one tag assignment from one tag to another tag, okay, I have to multiply all the numbers together and come back with the result. But I am saying that if the tags did not depend on anything, okay, all the tag assignments are independent of each other, this number would drop to 45 times 7. In this case, n is 7, right?
Right.
But in our case, our tags depend only on the previous case. Okay, that's why I am not giving you a very formal and very easy to follow proof here. But so the thing is that if I behave smartly, if I come up with a smart algorithm, there should be some kind of a complexity about 45 to the power 2 somewhere, and I'm going to repeat this n times. So that's what my complex is going to be. If I did not assume that my tag is not dependent on the previous one, but my tag, maybe it is dependent on t n minus 1 and t n minus 2. In this case, a factor of 45 to the 3, to the power of 3 will come into play, and that's the idea, okay? So that's what we are going to do with the dynamic programming, okay? Remember what we did when we do the dynamic programming with the shortest distance or the minimum edit distance stuff?
Yes.
We said that, okay, by checking all the possibilities up to some letter configuration, I can come up with always optimal way of achieving insertions, deletions, and substitutions, etc. by filling in a table. That's what we are going to do here. It's going to be a table filling stuff. So the algorithm is Viterbi algorithm, and it's the Viterbi algorithm because the guy who invented this is, well, actually many people invented this. It's not a very complicated algorithm. So you need to give a name to this algorithm.
The one that published it.
Well, I mean, there are other people who published this before him, but yeah. So and well, it's dynamic programming is not very difficult thing. I mean, if you assign this to a freshman or sophomore students, they can come up with it actually in a few days, some of them. But you need to like kind of channel them into through some ways and etc. It's not a very complicated algorithm, but again, actually, dynamic programming is Bellman. Bellman, you know Bellman, right? Bellman is way before than Viterbi in 1950s. But even before that, in 1600s, 1700s, people were using these kind of algorithms. Okay, so this is what we do. We are going to fill in a table like this, like we did when we do the minimum edit distance. So these are my columns. At each column I have words. Word number 0 is a dummy word. We don't have such a word. It's start word, and this is word number n, the final one. And I go to school early every day, etc. And every time I make an assignment to each of the words, I am doing this. For example, this is a verb, this is a noun, adjective, adverb, etc. Okay, so if I am picking this one, if I am this one, this is a pronoun. Okay, if I am picking this one, it's a verb, and it's picking 2 has its own class, right? If I am picking this, okay, right. So I am going to find a path. I am going to find a path from this end of the matrix to this end. Is going to be like this. Let me use a different color. Etc. And there is a path there too. Okay, so there will be a cost of transition from this position to this position. That's the transition probability, and there will be a cost of assigning this tag to this word. That's the observation probability. So at the end, I keep multiplying all these numbers together. The path that produces this, the smallest multiplication, the largest multiplication, will be my choice. That's what we are going to do. Okay, that's what we are going to do. Okay, let's do this. So this guy says that. Okay. Viterbo algorithm, you have the observations of length t. Okay, observations means they are words, and I have a state graph of length n. N is the number of tags. Okay, and I'm going to return the best path from it. So I will create a path probability matrix Viterbi n plus 2 and t. So n plus 2 times t matrix. At the beginning, I do this initialization. It says that from 1 to n. Remember, n is t is the number of words. I have t words, and n is the number of states. Plus 2 is for some dummy states, beginning and end state stuff. Okay, so I think I made a mistake here. I just did the opposite. We don't have, this is W1. This is W1, W2, and Wn. We don't have W0 stuff. Okay, so it starts. How am I gonna? Oh, let me get this out. Take this out. Did it fix it? Kind of. Okay, so we have, but let me keep compatible with what book says. This is T, right? T is the number of observations. Yeah, okay. T is the number of observations. N plus 2 is the number of rows. N tags plus 2 will be our first and last stuff. Okay, so at the beginning you just fill in this column of the matrix. It says that multiply. Can you read this? These are the transition probabilities from 0 to S. S is the state. So what is this? What does that say? A0S.
The probability of a verb start probability of verb.
A sentence. Probability of a sentence starting with a tag.
Yes.
Yeah. So, what is the probability of a sentence starting with a verb, with a noun, with a pronoun, etc.? Those are the stuff. And what is this then? BSO1.
Probability of that word being that bad.
But this one doesn't talk about word, right? It is BS. Probability of. Well, you are saying that observation. Yeah, exactly, that's true. Probability of B is the O1 is my observation. S is the state. Probability of that word being in my tag set, or probability of me assigning that tag to this word observation number 1. So I put them in the first column. Back pointers, I will come to that later. Then I have this two nested loops. It talks about from 2 to T. So it's going to be like move from this end to this end, from 2 to T. At the beginning, I handle this part first, and I'm going from 2 to T. But every iteration of this loop, okay, I need to go from 1 to N. I need to go like this every time. So I'm going to fill in all those numbers one by one. What does it do at every step? It says that for a given box as t, okay, t is the observation number, s is the state, choose, okay, this value. Check all the tag assignments of the previous word here, okay, that's the box, and multiply it with the transition probability from that s prime to myself, and choose the one, okay, choose the one that gives you the best multiplication, okay. Look at all the values in the previous column, okay. From any of them, calculate the transition probability times this observation probability. Whoever makes this largest, choose that value, okay. So that's what I do. So the cost of this calculation is, okay, cost of this calculation is checking of all the values in my previous case, and I'm doing this n times. So it's kind of n times t, n times t. Okay, again, ignore the back pointers now. After I am done, you do this calculation final time for the last column, and you will be done. Let's look at this example actually. This is going to be more understandable. Okay, so I want to race. Okay, and I like to assign one tag for each word. So what are very simple tag set. I have only 1, 2, 3, 4 tags. It is either noun, to, verb, or proposition, etc. Okay, so at the beginning, okay, remember I had n plus 2 tags. One of the tags is start tag, the other one is the end tag. Start tag, you have to start from the start tag and you have to end with an end tag, okay. The transition between here and this is this, okay. But let's get this number. What does it say? It says
1.0.
okay. What is this? 0.0 0.067. This is obviously this number. So I say that what is the probability that a sentence starts with a preposition or SS, whatever SS is, and this one is 1.0, okay. P start, because I am always at the I am always at this phase. It is P start, and that's what's going to be, and I get this multiplication. Here I am doing the same thing with this multiplication and this one, and I get all these, and I put them all these values here. So this value will be put in this box, this value will be put in this box, and this value will be put in this box. Okay, so I did this calculation at the beginning. Now when I come to this, so let's say our problem is just this much, okay. My sentence is just I, okay. If my sentence is just I, okay, in that case, which assignment would you choose? If my assignment is just I.
But here's a question. We didn't count for the I being a verb or preposition or noun, right? We just multiplied that a preposition comes after start times the start.
Well, P start is just a minute. No. It is 1.0. It's the transition there.
Oh, there's the one above the non-node.
No, this is just a transition probability, right? I mean, Previously I had this one. This is the transition probability. I didn't put any numbers in there yet, right? Did I put it in there? Yeah. No, I did not put that there yet because these are the numbers that you are talking about.
Yeah, now I have seen
Okay.
the notes.
So what is this 0? What is this? Maybe I asked that question too early. What is this number now? So this one is the probability of transition from the beginning of the sentence to this part, okay? Not just the probability between these two. Transition from the beginning of the sentence to this part times the observation. What is the observation? Observation is this.
I being a preposition.
I being PP or SS. Okay? It looks like I being a verb and I being a to and I being a noun is 0 because my data set is too small. I never have observed such a thing, such an assignment, so it will be all 0. So the same question again. If my sentence is just a one-word sentence, what would you choose? You, of course, the rest of them are 0. I would choose this one. Okay, 0.25. I would choose that one. Again, we never like any probabilities turning out to be 0 because nothing is 0 in this world. Okay, you have to have some kind of a probability. But in this case, our example is very simple. I didn't use any smoothing. It is like that. So when I come to here, that's what I'm going to do. For example, this one. I know all the transition probabilities from the beginning of the sentence to this by making these calculations. Okay? By making these calculations. What does this one say? It says, okay, V14 is this one, times probability of transition from noun to verb. Okay? I get this, and I multiply it, with this much. Okay, it is the place where I put this observation likelihood of want being a verb. Okay, so that's where it comes from, and for the sum from this one, I keep calculating this. So every time I am at this position, I run this one-dimensional loop, but I have many of them, so it makes a two-dimensional loop. Okay, it makes a two-dimensional loop, and then I keep doing this for each of the words that I have. At the end, when I come there, I know the largest probability of assignment, and if I keep these backtrace pointers, which words produced these maximum probabilities, then I can come up with the path that we are talking about. Okay, that's called the Viterbo algorithm. Very similar to, again, of course they have very different problems, but the idea is very similar. Okay, well, how did we do that in, I don't remember how we did that in the shortest distance or the minimum edit distance case. Did we fill in column by column, or did we fill in
row by row?
Did we fill in row by row, really? No, we can't fill in row by row. I think it was a special. We filled in, okay, this is what we did. We filled in first column and first row first, right? Then
Yes.
we filled in this. Okay, it was row by row, I guess. Yeah, it was row by row, like that. But we had to fill the first column and first row, because every time we make a decision, I had to know what is my left side says, what is my downwards neighbor says, and what is my diagonal neighbor says, right? So this one doesn't look at the same column data. It looks at the column on my left all the time. Just one. Okay, so idea-wise it's very similar. Build something, and principle of optimality again. Build something, and use whatever you have built, in your next step and continue this way. That's called the Viterbi Algorithm, and it works very nice. Okay, that's the summary of it. So it looks like I did the midterm exam a few years ago. I don't remember why I keep saying April. Oh, I remember that one. Yeah, that's the assessments, of course. Yeah. Okay, so the Viterbo algorithm says create an array with columns corresponding to inputs, each column rows corresponding to possible states, and sweep through the array in one pass, filling the columns left to right, column by column. And again, the dynamic programming idea is this. Okay, so it is in polynomial time again. So in polynomial time, let's look at this. Okay, 2 to t and 1 to n. It is n times t here, and calculating this max is important. Maximum of all of these, so n comes there too, so it is n times t. Again, polynomial time, not exponential time, polynomial time assignment to the tags. Yeah.
How accurate is this dynamic programming?
Well, it guarantees that you are going to find the optimal assignment. Well, everything depends on your data set, right? I mean, since we are using maximum likelihood estimation to assign the probabilities, and remember we assigned 0 values there. These are not very realistic. Why did we assign 0 values? We assigned it because our data set was very small and we didn't apply any smoothing techniques. So that's it. And the most important of all, remember these two guys. Where are those guys? Yeah. We made 2 simplifying assumptions. Each tag depends on the previous tag, okay? And each of the observation depends only the current tag. Each tag depends only on the current observation, not the previous ones. Because calculating this as it is not very easy. Okay, calculation is easy, but finding the data to estimate those probabilities is not that easy. So if this holds and if my data set is nice, then I should be fine. Okay, maybe related to your question, how precise is this, how correct we are doing, okay, maybe we should go and evaluate. Maybe that's what you are trying to say. How am I going to evaluate this? Okay. Well, and surprise for you, there is no part of speech in the real world, right? I mean, when you are talking English or Turkish, if you learned it from your parents, they never taught you about the verbs and the nouns and the adjectives, right? Unless they hold PhD degrees or some kind of a hobby of theirs is assigning tags to the words and etc. Okay? We just talk. We never talk about part of speech assignments to the words. Okay? These are all made up stuff, categorizations by the humans. Okay? Later. From the academia, from the higher education, whatever. Okay, so who is going to tell me that I am doing correct or not? I'm going to show them again. Did I do okay about this part of speech? That means that I can only race with the humans. Okay, and the bad news about this is that if you get 2 top PhDs about part of speech tagging, and if I make them sit and tag 1,000 words in a given data set, they will agree at most about 98% of the cases. 2% of the cases they won't agree with each other. I am not talking about the mistakes they are making. They are on purpose, they don't agree with each other. So if you say that I am 100% correct on this part of speech tagging, nobody will believe you because nobody is 100% correct. All you can say is that I am 100% compatible with this PhD guy, okay? But we don't know that he's doing correctly because other people are objecting to it. Okay.
What
So
about, is there some you know, many academic problems have standard test sets. So for example, computer vision or hyperspectral images have
yeah.
Avia Houston, things like that. What about this type of problem?
Well, I mean those computer vision problems. For example, if I take a picture of this room and ask you to mark the number of people, tell me. I would count the heads and I would say, this is the number of people. Okay, this definition is very, very well defined. What is an image of a human being? If I see the eyes and the head, that's a human being for me. So it is very difficult to make a mistake or very difficult to have a discussion about are there 3 people in this picture or 2 people? Okay, it is not the same thing. These are very vague definitions. I mean, remember the 45 tag set and the 80 tag set, okay, they cannot agree with what's a tag, okay, and it's a very rare that 2 human experts not agreeing on what's a human picture and not a human picture. And again, the remote sensing examples. If you don't agree that that pixel corresponds to a rural area or the or a building, okay, you just go and check there, right? So it is easy to find the ground truth. Well, I mean, you wouldn't say that the ground truth is 100% correct, but it will be 99.999% correct. Nobody will object. But with this kind of case, it is very difficult. And the same thing with the sentiment stuff. When you say with the sentiment type, thank you for bringing my dinner in 55 minutes. Is this a positive sentiment or negative sentiment? I ordered Getir, some food from Getir.com. Okay, so they brought me their food, my food in 55 minutes, and I posted this message. Thank you for bringing. I heard this one from somebody last week. Thank you for bringing my dinner in 55 minutes. I am doing a compliment, or this is some kind of a negative. Is this a negative thing or a positive thing? 5 minutes would be a compliment, positive thing. 55 would be. Well, again, you cannot be sure, because if I have ordered from the other side of Istanbul, 55 is not bad, right? Yeah. So, I mean, if I show you this, maybe half of the class will say positive and half of the will be negative. We don't have these kind of problems with the computer vision or some signal processing areas. We have this. So we call this human ceiling problem, right? Human ceiling. Human ceiling. Okay. And similar problem exists with the medical data. 2 different experts on the same problem, they say that this patient has pneumonia. The other one says that no, it's just a simple seasonal allergy, not pneumonia. Okay. So why are they so different? Because there is no definition of pneumonia or seasonal allergy proven for the cases of observations. Just a made up stuff, right? There is no pneumonia in the real life. We are just, if I this and this and this and this symptom. So I heard many times from the doctor say that there is no illness, there is patient. Okay, so you have the patients, and you observe your symptoms, and you take some action. You don't assign a single illness tag to your patients. If you do that, then from time to time you will be in error. Okay, so that's the evaluation. One evaluation would be this: why am I doing part of speech tagging? Can you tell me one example why we are doing this?
Computer translation, machine translation.
Machine translation. Okay. So for the machine translation, if I use a tagger that uses Viterbi algorithm, the other one uses the beam search. Okay. Put these 2 part of speech taggers into work under a machine translation, and measure the goodness of the translation, okay? And whichever produces better results at the end, you will say that, okay, this part of speech tag is better. Is it because it is better because of the algorithm or the tag set? I don't know. It is better. That's one thing. And we would look at this in a standard data set, confusion matrix. What does the confusion matrix say? It says the result had to be n, but I assigned in 0.2% of the cases I assigned the adjective. And the highest ones are, if you look at this one, highest ones are, okay, instead of nouns I assigned adjective, okay, instead of adjective I assigned noun. Those are high, okay. So if you look at this confusion matrix, this will give you some idea about your stuff. Again, gold standard is the compared with the manual coded results, and typical accuracy reaches 97%, and 100% is impossible even for human annotators. Okay, good. So that's part of speech tagging. We define the tags, we define the problem, and we model the problem in terms of probabilities against statistics is very important. And we talked about the bias rule again, and the Markov chain, hidden Markov model. And Viterbo algorithm is the final algorithm that assigns those tags to the given words in a polynomial time and polynomial memory. And that's it. Okay? So we did many things. So we talked about the words a lot. We talked about morphology. And we talked about the distances between the words and some dynamic programming. And we talked about assigning vectors to the words. After that, we moved up a little bit. Words are not in isolation. What happens in a sentence is important. So let's look at this part of speech tagging stuff, okay? Because if you don't look at the neighboring words, you cannot assign the correct part of speech tags, and we did that. And we are going to now move one level up. Now we will talk about sentences now. It's going to be parsing, okay? It's going to be parsing, and before parsing, I will have to talk a little bit about formal grammars, the grammars that you have learned in your programming languages course, and those grammars will be useful for us. And then how we can apply those grammars for the human language. It will not be perfect fit, but given the tools in our hand, this will be as good as we can do. Okay? But before that, let's take 15 minutes of break. 14:35, let's be here. And let's open the windows, please. Did everybody sign the attendance sheet? Attendance sheet? Hiçbir şey getirmedim yani.
Tükenmez yok.
Ne var?
Onu alacağız, biz numarayı alacağız. Öyle olmadı. Bunu buraya koyduysam bunun nereye gidebilir? Bunlar buraya gidebilir. Ama yine ona değil aslında. Sen yanında olsaydın direkt onu bu şekilde alırdım. Ne oldu? Nasıl define ederiz onu? Kardeşim ben olsam bunu çözüyorum, ona da hayır diyor. Bunu da yapalım. Ne? Tamam, bunu aldım. Bunu oynadım. En iyi hamle bu mu gerçekten? Bunun nesi var mı? Bunun nesi var? Mis gibi hamle olmuştu. Aşağı gideceğim. Nefes almaya. Hadi geliyorum. Kardeşim geleyim. Hafif dolduralım. Sivil havacılık gününü etkinliğe dağılır.
Hocam nasılsın?
Sen nasılsın?
İyi vallahi ne olsun yani. Koşturmaca.
Gene geldin mi?
Öyle. Herhalde bu son gelişim olabilir belki de. Bilgiyi tamamladım. Hoca geçen hafta sınav bir haftasında sayıyorum diye.
Aynen, sınavla beraber yediymiş.
İlk haftalarda onu tersini söylemiştim. Yani.
Aynen.
Ben de hiç söylemedim hocam böyle demiştiniz diye diye kabul ettim.
Ben bir böyle yöntemimi söyleyeyim sonra vazgeçtim. Dedim şimdi hiç şeye gerek yok.
Gerek yok.
Aynen.
Bulandırmaya.
Aynen.
Sonuç olarak şahidimiz yok.
Aynen.
Ama şeyi de sayması lazım. Yani bunu sayacak mı bilmiyorum yani. Değil mi? Kayıtlı yani.
Şahidimiz vardı ve dersi kaydı.
Valla ben yok ama kayıtta değildi gayet. Veya önünde konuşuyordu falan ama.
Kayıtta mıydı acaba?
Değildi yani. Ders anında değildi. Teneffüs arasında dinledik de. Şeyi de sayacağım dedi galiba değil mi? Bu iptal etti ya.
Aha, o şey, aynen onu sayacak.
Online yapacak.
Online derken ya şey gene sınıfta yapacakmış. İsteyen online yapıyor, isteyen şey.
Öyle hocam. Sen ne yaptın? Nasıl gidiyor?
İyi, ne yapalım?
Her şey yolunda inşallah. Sıkıntı yok. İyi var.
Ya 2-3 gündür hastaydım.
Öyle mi? Benim gibi bir şey yoksa başka
Yok
bir şey.
ya, çok kötü hastayım. Hatta test falan yaptırdım. Covid testi negatif çıktı.
Neyim var?
Abi böyle her yerim ağrıyordu ya.
Ama o Covid direkt.
Evet, negatif çıktı.
Öyle mi? Ya çıkıyor bazen hani negatifi geri
Ama
güvenme de.
iyileştim yani. 2 günde falan.
İyi. Ben de korona oldum.
Hı hı.
Hocam yani bende gram böyle bir grip belirtisi yoktu. Anlattım geçen.
Bende de grip yoktu.
Ağızlar şurası bile.
Her yer, benim her yer. Bir de mesela gece falan yaparken böyle titriyor falan böyle. Ateş, 2-3 kere hastaneye gittim falan.
Yani bir mikro kapmışsın belki belki başka bir şey ama
Soğuk,
soğuk algının belli.
yani test de yaptırdım hani Covid'se ona göre evde görüştüm
falan.
ama yok yani Covid negatif çıktı.
Yani negatifliğin şey oranı düşük.
Nasıl?
Test pozitif
False
diyorsa
negatif.
aynen false negatif olayı hocam sen daha iyi biliyorsun. Negatifin doğru oranı düşük yani. 3 kez falan yapman gerekiyor galiba yani böyle kesin bir sonuç alman için.
Valla 3 kez kim uğraşacak ya bir de zaten
Yani
devlet
devlet
hastanesinde
yapmıyor yani.
özelde yaptırdım o da
Öyle mi?
pahalı yani.
Niye özelde yaptın?
Valla hiç uğraşmak istemedim ya. Zaten hastaneye oraya gitmiştim. İşte onu yaptırdım. Şimdi devlet
sormasak ne kadar yaptılar test şu an?
160 ne yaptılar benim tüm hastanemde ama değişiyordur hastane hastaneye.
Değişiyordur. İyi, güzel. Güzel. Geçmiş olsun hocam.
Sağ olasın.
Ne kadar oldu geçeli? Geçen hafta mı?
Yani işte şey hafta sonu falan geçtim.
Koku falan test ettin mi?
Kokuda sıkıntı
Sen,
yok.
sen de geçen hafta da konuştuk ya.
Aynen konuştuk. Onlar aklıma geliyor. Hani koku falan diyorum. Hani böyle acaba kokuda bir sıkıntı var mı bakıyorum. Yok. Koku her şeyin kokusunu alıyor. Sıkıntı yok. Ama işte.
Yani bir karakteristiği var ya böyle o koku hasarısı normal gripte de oluyor ama hani ben geçirdim inanılmaz sağlık.
Ben de öyle. Kas ağrısı falan var.
Sonra bunu yaşamadım Allah'ta da tat krizine falan da çok neden oluyor. Sonraki dönemlerde.
Aşı falan da olduk yani. Bilmiyorum.
Zaten o muhtemelen hafif atlatmamızı sağlıyor.
Abi o an dönemi gelmiş. Geçmişler olsun.
Yani dün gece bitti ben.
Gece eklemiş yani.
Adam
Bunu açıklama yapmadılar.
tüm sistem programı chapter'da orada işte şeyler var, yine threadler, map'ler var.
Yani yoğunluğu da var.
Güzel ya, zevkli.
İyi ders abi ya o an.
Ama değil.
Güzel dersler.
Çekilir bir ders yani.
Valla
Digital'da da var mesela. O da öyle. Güzel ders yani. Biraz işimiz çok ama keyifli ders. Ben digital image processing alıyorum.
Alıyor musun?
Harcamak.
Orada nasıl? Buraya matematiksel mi?
Yani kanka matematiksel çok fazla zaten. Bütün işlemler şey yani. Lineer algebra gerektiriyor.
Kosinüs, sinüs falan öyle şeyler var mı?
Trigonometri çok yok kanka.
Çok yok yani.
Lineer yani lineerce bir aldık ya biz. Yani ikinci senenin baharında aldık işte. Tam pandemiye de ilk gelen ilk dersler. Matematik dersi pandemiye denk geldi. O ders yani.
Burada.
Sen saydın mı onu? Almadın mı?
Yok. Ya onu aldım da.
Evet.
Ya o dersten vardı.
Bayağı onu kullanıyoruz genelde.
Ödevlerden kağıt üzerine mi oluyor?
Abi latte çıktı şey yaptı. Matematiksel çözüm ne latte yaptırıyor. Kod istemedim şu ana kadar hiç.
Kod yok ama program var.
Yani kullanıyorsun. OpenCV kullanıyoruz zaten.
Sınava girdiydim.
Sınava girdik kanka. O da matematikti genelde.
So today we will look at the concept of parsing. For this, we are going to use this context-free grammars. You are familiar with context-free grammars because we keep using context-free grammars for our most popular programming languages such as C, Java, and then we are trying to associate this grammar with our natural languages. They won't be powerful enough for the whole language, but we like these context-free grammars because we have very nice parsers for them, very efficient parsers for them. We understood them better than the other grammars, and that's why we will spend most of our time around these context-free grammars. Then we will look at this grammars of English, what kind of grammars we can have, tree banks, and then we have this dependency grammars other than the context-free grammar. It's a different type of grammar, sometimes useful for the natural languages, especially for languages such as Turkish. Okay, dependency grammars. They say they are better than the context-free grammars. Okay, so let's move on. Let's start talking about it. Okay, let me skip this one. Okay, why do we care? Okay, why are we doing this? Remember, for the part of speech tagging, why do we do part of speech tagging? We do it because it is required for some question answering systems. It is required for machine translation, text to speech applications, etc. Similar stuff. Most straightforward usage employment is the grammar checker. You check if your grammar is okay. If you write a sentence in an editor, okay, you check if the grammar is okay. Dialogue management, when you are producing sentences, of course, they have to be parsed correctly, question answering, information extraction, and most importantly, maybe the machine translation, okay? So when you parse a given sentence, you understand what that sentence grammatically, and when you produce another sentence in the other language, you have to go through the same phases, okay? So especially for the context-free grammars, we will keep talking about this concept of constituency, okay? What it is and why we are doing it, why we need it, and how we are using it. And then again, this dependency is important, and we are going to look at it later. And context-free grammars, and as always, if you are doing statistical natural language processing, machine learning based natural language processing, we need to look at the resources, our data sets. We had the data set for the engrams, we had the data set for the part of speech taggers, and we have the data sets for the tree banks, especially for English. Okay, so let's look at this constituency, the thing of constituency. Okay. Remember what we said about part of speech tagging? We said that for each word we can assign a tag. We say that this word is a noun, this word is a verb, this verb is such and such. Okay, so we are giving some categories for each of the words, and we don't actually try to bring together the words and give them names. Okay, constituency kind of does that. Okay, what kind of groupings can we do? Can we do between the words? And if we can do those groupings right, can we give them new names? Can we categorize them under the same title? Okay, so this is done in all the natural languages. Okay, so you put together a number of words occurring in a sentence. Okay, nearby words, neighboring words, and you say that okay, these are grouped nicely. These are grouped nicely because they have some internal structure, and when I group them, they behave in a certain way with respect to the other units in the same sentence. So they have internal structure, and their relationship with the other units in the same sentence can be defined very well. Okay, very well. So maybe without going further, I should give you one example. For example, look at these chunks of words. Harry the horse, the Broadway coppers, they, 3 parties from Brooklyn, the reason he comes into the hot box, etc. Okay, these are all called noun phrases. Okay, again, they are groupings of words. They can occur in a sentence. Okay, their internal structure can be defined, and they can find, since these are noun phrases, that they can be, for example, 3 parties from Brooklyn is here. So, and it's like she is here, or 3 parties from Brooklyn is here. So I can replace 3 parties from Brooklyn with a she. So the sentence is grammatically okay. So this is a constituency. It behaves like a noun, and we call these kind of constituencies noun phrases. Okay, and noun phrases might have some complicated internal structure. Nevertheless, we can group them together and call them noun phrases. Again, this is different from part of speech tagging. In the part of speech tagging, we assign a tag for each of the words. Now we are trying to put together words, and we call them these kind of names like the noun phrases, word phrases, and etc. We are going to see what kind of other constituencies we have, and no exceptions. In all the languages, we have these kind of constituency definitions. Okay. In Turkish, we have the similar groupings. We sometimes, what do you say? We have isim tamlaması, sıfat tamlaması, etc. For the verbs, what do we say? Fiil grubu, etc. So everybody makes these kind of definitions for their own languages. And if you think about the formal languages, such as the programming languages, if I put a number of statements together in a special way, sometimes I call them functions or classes, or I call them loops, and etc. This is something like that. Okay, this is something like that. So why do we call them noun phrases? Because because I can put any of them before a verb, right? Okay, Harry the horse is fast. Okay, they are welcome. So that's the external evidence, because I can put this chunk of words, the group of words, in place of a noun, and that's the external evidence for me. For the internal evidence, they have to follow some rules. Okay, they have to follow some rules. Okay, for example, the determiner noun rule, or determiner adjective noun rule, etc. So that's the constituency. If I come back to this one again, if you are forming some kind of a constituency, it has this internal structure defined by formal rules. Also, their external behavior should look like, if it's a noun phrase, then it has to come before the verbs and etc. Okay, so that's the idea of constituency, and our formal grammar, especially the ones that are using the context-free grammars, will depend on this idea of constituency. Okay. Well, as I said before, these are all categorizations done by the academicians about the languages, and sometimes they have disagreements, and sometimes it's not that easy. Okay, there is nothing easy or obvious about how we come up with right set of constituents. So this is more problem, even a tougher problem than the tag set for the part of speech stuff. This is even more difficult. But if we do that, if we start from some point, the final output will be valuable because it's going to be parsing. We are going to parse the whole sentences, give grammatical meanings to the whole sentences. And if there is an ambiguity in the grammatical meaning of the sentence, and we need to find it, and we can say that I can parse this sentence either this way or that way. Okay. So there are many different theories about what a grammar should be, and how we parse a sentence, and etc. And there is no right way to parse a sentence, and there is no, I mean, we say that we speak Turkish or English using some grammar rules, which is not correct, because it is correct up to maybe 95% of the time. Even the most formal speakers, okay, they make up their own grammar rules, and some of the sentences they are used, they don't follow the standard grammar of the language defined, okay? Because as I said, nobody designed our language, Turkish or English, okay? After it is spoken, it is used, somebody came up with the idea. It's the same as when Newton came up with this formula for the object's motions, okay? Objects don't move because the formula is there, okay? It's just Newton's idea to model the motion of the objects using this formula. And it kind of works. It doesn't work all the time. It doesn't work for the very small objects, particles. It doesn't work for the very large objects like the galaxies and etc. But for the real life stuff, it kind of works, and we take it. It's just a model, okay? So the grammars are just a model for our languages, Turkish or English, okay? And if a sentence doesn't obey some of the grammar rules, and that's okay, because that sentence is spoken, it is understood by some people, and we wouldn't say that I am rejecting this sentence because it is not grammatically correct. No, we don't say that. Okay, we don't say that. Like we don't say that I am rejecting the motion of this particle because it doesn't obey the Newton's third law. We don't say that, right? Just Newton was wrong in that case. Okay, so that's what we are to do. So that doesn't mean that this is not a very valuable contribution. Of course it is. It is helping us a lot. This is much better than not having anything at all. This explains lots of stuff. All the mechanical stuff that we use in this world is based on this stuff. Okay, all the cars work that way. Okay, all the moving stuff work using this stuff, and all the buildings are designed using this formula, and etc. So it is very, very valuable for small things, and for large things, well, they are not critical anyway, so we can think it that way. So we are trying to come up with a model, okay, that will explain our grammar, our syntax of the sentences, and we will accept the fact that it will not work 100% of the time. Okay, that's good. So we will have computational problems, constraints. We will have the definition of the constituents and etc. and other stuff we are going to see in a few minutes. Okay, so let's talk about this context-free grammars. But before we talk about context-free grammars, let's go to Chomsky hierarchy, and let's try to remember what the Chomsky hierarchy was. Is Chomsky alive? Is he alive?
No.
He's dead? Well, he was making lots of noise a few years ago about Turkey. We don't like him much in Turkey. He's good.
He's alive.
Yeah.
92 years old.
Well, he's still young. He's 8 years before he's called. He's becoming old. Okay. So Chomsky, when he was much younger than 90 years old, 1956, Okay, he said that we are going to define grammars and it's going to be hierarchical. Okay, this hierarchy, type 0 grammars, type 1 grammars, and type 2 grammars. Okay, all the grammars will be defined by this three sets: finite set of non-terminal symbols, finite set of terminal symbols. Terminal symbols are our words, if you like to think it that way. Our words are terminal symbols. Non-terminal symbols are the names that we give to the constituencies and a star symbol. Okay, for example, this is a grammar. Small case letters A and B are our terminals, and this is our star symbol. So can you tell me one sentence that can come out of this grammar? A, B, A, S, and this B, S, and
small a, B.
Oh, just an A is just an A okay? Just an A?
No.
No, A has to be at the beginning. Well, I can. Oh, yeah, I can write it there. Okay, A has to be at the beginning. Okay, no, it doesn't have to be at the. It has to be. Yeah, and A is here. Then S. Well, and then B. This is one example. A B, right? And then A B. It looks like that, right?
Only A will
I
be
think
enough. I
A,
think.
B is not enough.
Why?
No, A B is good, right?
No,
A S
There's
S
epsilon.
then B and B, right? It's
Oh,
like
S can be an empty string.
yeah, S is an empty stuff, right? So this grammar is as powerful as a regular expression, I guess. I can parse this using a finite state automata, right? A and then B. Okay, so this is simple enough. Okay, so just an example. So the Chomsky says that. Okay, I can write these kind of grammars for the natural language or other stuff. And the thing is, my hierarchy is going to be this. Okay. There is one large, very general type of grammar, recursively enumerable grammars. It is type 0, and then context sensitive, context free, and regular. Regular grammars, we looked at it. These are the grammars that can be parsed using the finite state automata. Okay, finite state automata. Then we have the context free, then context sensitive. Let's look at this regular stuff. Regular. Okay. Expressions, regular grammars, type 3. Finite state automata can parse them, and this is the set of rules. Okay, it has to be either A is going to a terminal or some terminal and non-terminal. Okay, so that's it. You cannot say A goes to B, A, and something. Okay, so this is not in the type 3 grammar. Okay, this is not. This is bad. Okay, so we already looked at it, and we said that finite state automata, finite state transfers, the same thing, are good enough for us to handle most of the morphology with the natural languages of the words of the natural languages. Okay, so that's what they did. And then we have this context-free grammars. Context-free grammars say that, okay, on the left side you will have a non-terminal. On the right side you can have anything you like. Okay, it could be parentheses A plus B, parentheses again. It is all terminals. Or it could be parentheses, another non-terminal, and then parentheses again. So you can combine terminals and non-terminals on the right side. Okay, this is called context-free grammars. And all the programming languages that we use, they depend on this grammar most of the time. Sometimes they have to make exceptions, but because context is not important for them, but sometimes the context is important. Most of the time it is not important, we can parse them. After parsing them, we handle the context later. Okay. And this one is about context sensitive languages. These are the rules. Okay. So I can, if I need to, I can put any expressions on the left and right side of the left side of these rules, and on the right I can do anything I like. Okay. So did you see that? Why did you see why they are calling it context sensitive? It says that I am going to apply this rule if I see it within this context. If I see alpha and beta before and after this A, I can apply this rule. Okay? So it talks about the context. This one doesn't want to know what's happening around A. This one knows it. So that's why it is context sensitive. Okay, to parse these kind of stuff, okay, your regular compilers will not work. Linear bounded non-deterministic Turing machine will solve it. Okay, this one will be non-deterministic push-down automata. Okay, and then no restrictions for the left and right. Anything can happen on the left and right. So you need a Turing machine. You need the power of a full computer to make this parsing. So parsing of such grammars will be difficult. So and your algorithms can take exponential time and can take exponential memory. Okay, we like these because because we have very nice algorithms for these two. So we like to stay at the context free side. Okay. Sorry, we like to stay at the type 3 side and the context type 2 side, and let's talk about, so type 2 grammars are the grammars for our programming languages. LL parser, linear time parser, very efficient, very smartly designed parser. And Turing said all of these, and in 1956 it was way ahead of his time. In 1956 they just started using the transistors, right? So of course he was considering the computational models for this, but theoretically, for the linguistics wise, it was all good. So let's go back to our slides again. We are going to do the context free grammars. That is, this guy is going to the so on the left side you are not supposed to have anything other than the non-terminal. On the right side you can have anything that you like. Okay, so we have rules, we have terminals, and we have the non-terminals. We have the terminals, again the words. Non-terminals are constituents, that will be constituents, and rules are each rule that is having a left and right side. On the left, for the context free grammars, you can have only a single non-terminal. Okay, so let's look at some of the rules for the constituencies, some of the noun phrase rules. Okay, noun phrase is a constituency. I can place a noun phrase instead of a noun in a sentence, and that sentence will still have grammatical meaning. Grammatically it will be okay. So for a noun, okay, by the way, if an element starts with a capital letter, it's a non-terminal. If it is a small case letter, then it's a terminal. So noun phrases could be determinate nominal, or it could be proper noun, or it could be noun, or nominals could be noun or nominal noun. Okay, so that's one set of rules to define the noun phrase constituency structures. So if you notice that this is a recursive stuff, it is okay with us in terms of context free grammar rules. No problems here. Okay, so recursive I can define it. Very, very, very long noun phrase. Okay, and this kind of the base case for the recursive rules, and it could be very, very, very long. People usually, human beings, people usually don't use more than 2-3 levels depth nominal names, and we are going to see it in a few minutes. Okay, using these stuff, let's look at this very simple zero grammar. Okay, obviously it's a context-free grammar. On the left, I have the non-terminals. On the right, I have terminal combinations. A sentence is a noun phrase and a verb phrase coming together. One constituency is here, the other one is here. Okay? A noun phrase could be a pronoun such as I, okay? Or a proper noun such as Los Angeles, okay? Or a determiner nominal a flight. Nominal could be a noun or nominal noun, okay? Nominal, so nominal could be a noun. So recursive, I could say morning flight or early morning flight, early morning cheap flight. See, I can put all these words one after each other. It makes a larger nominal. Larger nominals makes larger noun phrases, and my still works. Okay, early morning cheap and fast and something flight. Okay, again the whole thing makes another noun phrase. Okay, that's the advantage of having a recursive rule. The same thing for the verbs. Okay, a verb phrase could be a simple verb such as do, or verb noun phrase I want a flight, or noun phrase propositional phrase. Okay, I want him to go there, such as that. Noun phrase propositional phrase, or verb and propositional phrase, leaving on Thursday. You want to go there, etc. Want to go. Okay, so these are the verb phrases. Then we have the propositional phrases, preposition and noun phrase from Los Angeles to Los Angeles, and in book, outside of something, etc., etc. So these are the propositional phrases. Very simple grammar. Very simple grammar, but it is good enough to parse non-question, non-imperative sentences, and as we said, this is a zero grammar, primitive grammar, and we are going to do a little bit better than that. But we will use this to give you some examples. Okay, like the finite state transducer or finite state automata. Okay, we can use these kind of grammars to generate syntactically correct sentences. Okay, generate strings in a language. I can use it to generate strings in the language. Start from this one, and for example, as noun phrase, verb phrase. For the noun phrase, I am going to, for example, use a pronoun, and for the pronoun, I will say I. For the verb phrase, I will use a verb, and from the verb I just say go, I go. Okay, just a sentence. Stupid, simple sentence, but I just generate a sentence. Using these kind of derivations, you can generate sentences that are acceptable in this language of English. Okay, so generativity generates strings in the language. Also, I can use it to reject strings that are not in the language. For example, it is not possible to parse this sentence I. Okay, because for the S to happen, it has to be noun phrase and verb phrase. I can make a noun phrase on the left side, but on the right side there is no verb phrase, so I cannot parse this sentence with this grammar, so I am going to reject this sentence. I will say that this is not in English. Okay. More realistic sentence here that is possible with the grammar that I introduced. I prefer a morning flight. Okay. Again, Sentence, noun phrase, verb phrase, noun phrase, pronoun, verb phrase, verb, noun phrase. Okay, noun phrase, determiner, nominal, nominal noun, etc. Everything is there. So these are all terminals. Rest of them are non-terminals. And I prefer a morning flight. It's a very nice parsing tree. Okay, this is a parsing tree. If I am translating from one language to another language, from English to Turkish, okay, from English to Turkish, here is my, English is subject, verb, object language, right? And Turkish is subject, object, verb language. Verb is at the end. So here I know this part is noun phrase and this part is verb phrase. And I can keep this I at the beginning then. Okay. But when you say verb object, that is this part, verb object, I prefer a morning flight. So prefer should be at the end for Turkish. Ben sabah uçuşu tercih ederim. Okay. Tercih ederim ve goes to at the end. So I'm trying to tell you that how useful this is for doing the translation between English and Turkish. Okay. All you are doing is just after the parsing, you are taking this part to the end. You are keeping this part maybe in the position and this one, and changing the words from English to Turkish, and that's it. Good. So those are the derivations. So let's look at, okay, we already did that, the definition of the context-free grammar. For stuff, non-terminal symbols, okay. So the non-terminal symbols depends on actually the language grammar, and it's going to change from grammar to grammar. And there is no single grammar defined for Turkish or English. It changes from export to export. And then we have the terminal symbols. Those are the words, okay. Those are the words, and this set and this set are disjoint. There is no common element between them. And R is our set of rows like this. On the left side, I have only the non-terminals, and on the right, it is anything. And we have a start symbol. We have to start from somewhere. Okay. Okay, so that's the definition. Parsing is the process of assigning one or more parse trees for a given string. Okay, so it is very similar to running a finite state transducer with a tape, but it's more powerful because there are some things that the finite state transducer cannot do. For example, this is a very S, parentheses, S, and this. You can't do this with a finite state automata, finite state transducer, right? Because remember, for the finite state transducers, your rules are like this, A and B. It forgets about this A when you start doing this B, because you cannot put any terminals at the end of the rule. This one can. Okay, so balancing parentheses using a finite state transducer is not possible. You cannot balance it. But with this one, it is okay. It is possible with the context-free grammar. So context-free grammars are more powerful than the regular expressions or the finite state transducer. But with the power, there comes the problem of algorithms, because our algorithms for the context-free grammars will be more complicated. Okay, so we looked at that L0, and we are going to look at some other examples of grammar and the sentences. Okay, this is a different grammar now. Previously we did that. Okay, these are all different additions for the start symbol sentence. noun phrase, verb phrase, a plain left. Okay, these are imperatives. Okay, just leave. These type of sentences doesn't have noun phrase at the beginning. Question sentences, auxiliary noun phrase, verb phrase. Did the plane leave? Okay. So you put auxiliary. How about WH questions? The questions that start with a who, where, when, which, etc. So you put WH at the beginning and auxiliary, noun phrase, and verb phrase. Okay, so these are the four basic sentence types of English. We are not saying that these are all, but these are some of them. Okay, noun phrases is the complex part of English because this is a noun phrase. Okay, all the morning flies from Denver to Tampa leaving before 10. It's a noun phrase because why it's a noun phrase? Because I can put this in a sentence. Okay, flight cancelled. Flight is cancelled. Instead of flight, I can put this in there because it's a noun phrase. It's a noun phrase too. All the morning flights from Denver to Tampa leaving before 10 are cancelled, but let's ignore that agreement thing for now. Okay, so it can get very complicated, but context-free grammars are powerful enough to parse these kind of complicated stuff, and that's the parsing tree. Okay. Noun phrase, predetermined noun phrase, determined nominal, nominal gerundive VP, nominal PP, nominal PP, etc. All the morning flights from Denver to Tampa leaving before 10. We call these flights here. Okay, this noun phrase is about flights, right? It's about flights. Flights are cancelled. What kind of flights? All the morning flights from Denver to Tampa will be leaving before 10. Okay, so this context-free grammars are powerful enough to parse these kind of noun phrases, and well, I mean, it's a matter of writing your rules right. Once you write your rules right, then you should be okay for most of the time. That flight thing is the head of the rule. Okay, this NP is about flights. Your sentences are about verbs. Okay, the flights are cancelled. The important thing in this sentence is the cancelled. That's the verb. Okay, so verb is the head of the whole sentence, but for this noun phrase structure, the head is this flight. Okay, for this propositional phrase, the head is Denver. Okay, for this gerundive VP, okay, the head is leaving. Okay, so so the definition of a head in a given rule is fixed. You don't make any complicated artificial intelligence decisions. It is all fixed. Okay, so we are going to talk about these heads later when we talk about dependency grammars. Okay, so these determinants are not that difficult, as we know. I mean, the number of determinants are fixed. There's a and etc. Okay. So yeah.
Here again, we are assuming that we know every word's label or whatever.
No, we don't. No, we don't assume that. No, we are saying that we know the part of speech tags for each word. No, we don't. Because if we know them, that means that there wouldn't be any ambiguity of the most of the time of the syntax trees, but there will be. Okay.
So in order to make the previously talked about tree, we need first to do the part of speech analysis, and then
Well, part of speech analysis doesn't mean that we know what tag I am assigning it. Maybe it means that we know what kind of probabilities I am assigning to each tag. Okay. If I know the probabilities of each tag for each word, then I can use those probabilities to assign probabilities to parse trees. Okay?
Oh.
So parse trees, again, there is always ambiguity. We have ambiguity in morphology, we have ambiguity in part of speech tagging, and we will have ambiguity in parsing. Okay? I can parse the same sentence in many different ways, right? In many different ways. So which one I am intending, I don't know. It depends on the context, but I don't have the context. So I'm going to report. Okay, I have 3 parse trees for this sentence. This one, this one, and this one, and these are the probabilities if I have it. Okay. So we are going to see some examples of it. And this is a very before I forget, this is a very classical example. Let me show you this, and let me take a break after that. Maybe I showed you this before, but that's okay. I see a man with a come on, this is a okay, good. And images. I see a man on a hill with a telescope. This is the classical example of, okay. I see a man on a hill with a telescope has 1, 2, 3, 4, 5 different parse trees. This might be the case. I see a man on a hill. The man is on the hill. I am with a telescope. I am looking at it with a telescope. Or I am on a hill with a telescope and I am seeing a man. Okay. You understand this, right? 5 different meanings.
Yeah.
Translate this into Turkish. Tepede teleskoplu bir adam gördüm. Ha? Tepede teleskoplu bir adam gördüm. This one. This one is tepede teleskopla bir adam gördüm.
Teleskoplu tepede.
Teleskopla tepede bir adam gördüm. It's kind of in Turkish it is ambiguous too, right? When you say teleskopla bir adam gördüm, it doesn't say that if telescope belongs to me or to the
Teleskopla tepedeki adamı gördüm.
Teleskopla, well, if they wanted, they can express the same sentence with less ambiguity if I put my words more carefully, but this is done on purpose, right? Of course, in Turkish there are ambiguities, in English there are ambiguities. Our ambiguities do not correspond to each other, but ambiguity. So, each of these cases I am using the same sentence, okay, I am using the same sentence. Part of speech tags are the same too, okay, but their parse trees are way different. Do I have the parse trees here? Let me maybe, okay. Parse trees. Which one? Yeah, this one is good. I saw the man with the telescope. Let's forget about the hill. And I'm going to ask you to translate. I am going to ask you to where did it go? Somebody's slides. No, I don't want to do that. Yeah, maybe this one. Okay, let's make this. Okay, let's do this. I couldn't make this any. If I go there, it is just PDF document. Maybe I can go there. Slide handout, something. Oh, okay. These are the same slides that I am using now. Yeah. Let me show you the tree. Okay, good. No, well, this is good too. I ate the spaghetti with chopsticks. Both sentences, okay? Translate this one and translate this one into Turkish. After we come back. We will come back. We will come back in 15 minutes. It is 35. Okay, 15:35.
Kötü. Senin?
Niye kötü senin?
Gitmeye yaklaşıyor.
Bitirmeyi kimden alıyordun?
Yıldız.
Konu nedir?
Okul uygulaması.
Ne uygulaması?
Okul uygulaması.
Bitcoin.
Bir Bitcoin.
Nasıl ya? Dijital de hani. Fizikseli var.
Ve şimdi bunu da şey alıyorsun. Bir USDT. Temiz.
Bir USD.
Bir.
Ya bu normal bir Bitcoin şeyine gelmiyor yoksa?
Yoksa beni şimdi kaç kere bıçaklarlar böyle 50K'dan bahsediyoruz.
Olmuş ama.
En son 50K'ydı. Bakalım.
İlgileniyor mu böyle? Oynuyor mu yatma?
Tabii ki de oyun
Kazan
oynamayacaksak,
oluyor mu?
oyun oynamayacaksak nerede var?
Yok şeyini diyorum yani. Yani Bitcoin'e falan.
48,5.
Hı?
48,5.
Yatırım yapıyor mu diyor.
Yapıyordum da işte en son çok güzel bir düştü. Tamam mı?
Orada kaybettim.
Üşenmesi. Sonra dedim ki Tether'da kal boşver.
Abi bir şey yapmak lazım ya.
Hı.
Yani bilerek yatırım yapmak lazım. Öyle şey değil de şans olarak.
Allah. Ben sanki bilerek yatırım yapmıyorum.
Hayır yani senin için demiyorum da mesela Bitcoin'e yatırım yapan çok insan gördüm. Hiç böyle mesela blockchain'e nasıl çalışıyor?
Kardeşim
falan
ben
hiç
direkt
bilgisi yok yani.
ekonomist arkadaşımın desteğiyle yaptım bu işi. Ona rağmen patladığını sen oldu işte görüyorsun. Nasıl ya? Gördün mü? Çok büyük oldu çünkü belli oluyor. Normalde şöyle. Belli oluyor.
Dolara ne abi? Altın al dolara.
Dolar değil mi? Tether işte.
Hı?
Shit.
Benim param yok olacak. Yoksa nerede alacağım?
Al Tether al. Bir şey söyleyeyim mi?
Tether,
al.
Ethereum mu?
Yok.
Ne?
USD Tether.
O ne?
USDT. Şöyle ki bir Tether her zaman $1 eşit. Yani şimdi diyeceksin ki lan oğlum Fatih o zaman niye direkt bankadan almayayım ki? Mal mısın? Ama şöyle bir şey var. Bankadan aldığın zaman banka senden çok çılgın
Şey oluyor.
şey kesiyor, makas kesiyor. İnşallah. Gördün mü?
Okay, so this is not exactly the same example that I like to share with you, but this is okay too. The sentence structure is very similar. I ate the spaghetti with chopsticks, and I ate the spaghetti with meatballs. Okay, so depending on of course the context, we understand which one we mean, and their structure is different. See this. This one is verb, noun phrase, propositional phrase. This one is verb, noun phrase. So the spaghetti with meatballs is the noun phrase itself. Here, spaghetti with chopsticks is not the noun phrase, it is a verb phrase. So noun phrase is the spaghetti. With chopsticks is part of the verb phrase. By doing this, okay, when you translate them to Turkish, okay, you translate them very differently. I mean, you don't translate them into two sentences that differ by one word only, right? But how would you translate them into Turkish? I ate the spaghetti with chopsticks. Makarnamı çubuklarla yedim. What do we call this in Turkish? Ne diyoruz onlara ya? Çubuk. Çin çubuğu. Yok ya şu şey var ya, Çin'den yedikleri çubuk, chopstick onlar.
Çubuklar değil mi?
Çubuk mu? O kadar mı? Makarnamı çubukla yedim. Kıymalı makarna yedim. So very different sentences. Okay? Very different sentences. Without parsing them, you wouldn't know that. So, I mean, it looks like I'm going to change one word in the sentence and the translation will be okay. No, it is not. So it will change. It will change. Go back to the slides. Okay. So we talked about the determiners. Okay. Simple lexical items like an egg card or John's card, etc. These are the simple stuff. The complicated stuff for English are the nouns and verbs. Noun phrases, verb phrases. The noun phrases are more complicated. Okay, with the nominals we have the pre and post modifiers. 3 cars here is the pre modifier. For the post modifiers, okay, from Seattle, okay, for example, the flight from Seattle, okay, flights arriving before noon, etc. These are the post modifiers. Okay, and this part is kind of, I ignored it, but let's talk about it. Okay, I said that noun phrase and verb phrase. Okay, is a noun phrase, right? Then I say or let's say this one is a verb phrase, verb and goes is a verb which is a verb phrase, and I can connect it to a sentence. Noun phrase, pronoun, and I. It looks like I parsed this sentence, I goes, but it shouldn't be parsable. Grammatically it is not correct. There is no agreement between subject and the verb, right? So how am I going to do this? Okay, so the agreement should be inside between the noun phrases and the verb phrases. Agreement should be within the noun phrase itself. I mean, you wouldn't say this flight or those flight. You would say this flight and those flights, right? So the agreement should be satisfied, otherwise grammatically these are not correct sentences or correct phrases. What are we going to do with the context-free grammars? This is what I do, noun phrase and verb phrase. So we have to make some changes to our rules, maybe, okay, because we are over-generating, okay? This one generates I go, I goes, right? We go, we goes. This is over-generating. This grammar is generating some sentences that are not in English. This is called overgeneration. Okay, so such a rule set is overgenerated and we don't like it. We don't like it. So what are we gonna do? The similar stuff is here too. Okay, some verbs are used this way. Okay, just disappear without any objects. Somebody disappeared. Okay, he disappeared. Sometimes it is with a noun phrase. I prefer a morning flight. This is a noun phrase. Okay. Sometimes a noun phrase and propositional phrase. Okay. The leave first thing in the morning. Leave. This is noun phrase and this is propositional phrase. Okay. Again, this is another propositional phrase. So these are very different structures, different sentences, and the words that are used with these kind of sentences are different. Okay, you cannot switch one word with the other one. Okay, and you will say, for example, disappear. Okay, you cannot switch leave and disappear. Okay, you cannot say I prefer dot. There is no sentence like I prefer period. No. You have to say you prefer something. You have to put an object with it. You have to put another noun phrase for it. But yet these rules don't tell you anything about those. So what are we gonna do? We have to give arguments to those kind of rules. So that's going to be subcategorization. Come up with a different set of rules for different set of verbs. And if you do that, you will end up having hundreds or more classes of verbs and nouns and different specialized rules. And if you do that, you will end up having thousands of rules in your grammar set, which will be very difficult to deal with and difficult to document and difficult to talk about. Okay? So what are we going to do? For now, we are going to ignore these kind of problems. We are going to ignore that this is over. John sneezed. Okay, this is good for the sneeze, but for the find, you have to have a noun phrase that is agreeable with find. For the give, you have a noun phrase and noun phrase. For the help, you have a noun phrase and proposition phrase, etc. We know what kind of rules are applicable for these kind of words. You don't say John sneezed the book. Sneeze verb doesn't take any object, okay? Or you don't say give with a flight. With a give is not used with this kind of structure, okay? So use the correct subcategorization. But if I do that, almost for all the words, there is a special use case scenario, and I don't want to list all of these rules in my grammar set. That would be too much to talk about them. Again, let's ignore this problem for now. Okay, we can deal with these later, and we can deal with these later, or you can find some other solutions. The same thing here. Okay, this is a valid C statement, right? This should be parsed nicely. Okay, there is a nice parse tree, and in this nice parse tree, I can parse this, and this should be okay. But if you consider the context, what happens if I is for example, a vector? This shouldn't work, right? It is possible, but this shouldn't work. So this is only available, this plus is available only for maybe integers and doubles and that kind of strings and that kind of stuff. It is not available for the vectors. Okay? But at the beginning, I am going to let my compiler parse this into a tree. Once I realize that it is trying to use operator plus on this I will signal an error message, and I'm going to do the same thing maybe for this. Okay, so let's ignore this problem and let's consider the natural languages are easily parsable by context-free grammars without much configuration. Okay. Well, I mean, what did I say at the beginning? With our programming languages use the context-free grammars, but they use more than that. Okay. After parsing, they have to do this kind of checking. Okay. What is the type of I? If I is this type, this parse tree is acceptable, but it is not. Okay. And sometimes it becomes ambiguous. Okay. Two different kinds of parse trees, and I get the result from the definitions of the variables. Okay. Your programming languages, your program that you are writing cannot be an ambiguous program. It has to have a single meaning. Otherwise, it is not compilable. Okay. So if you are producing two different parse trees for a given statement like that, okay, maybe you can resolve the ambiguity by looking at the definitions of the stuff. For example, if I is integer, the meaning of plus is different. If I is a double, this is different. And if I is a string, it is very different, right? So I don't produce more than one parse tree, but I change their meanings, and we have ways of dealing with it. All I'm saying is that context-free grammars are not by itself sufficient to do this kind of parsing. You have to do some post-processing after the parsing, which is very easy for the programming languages, but it is not that easy for the natural languages. Okay, so right now various rules for VPs overgenerate, and we are going to stay this way, and we are going to ignore this problem. Some people say that why don't we come up with a set of rules, some of them for the singular use, singular sentence, singular noun phrase, and singular verb phrase. So you cannot say I goes. It has to be I go, right? And I do the same thing for the plurals and do it that way. But again, I mean, the agreement between this, the singularity is only one way of agreement. There are many other stuff like the types of the words and etc. So let's ignore this problem, because the solutions are really ugly. Lots of rules need to be written. Some of them we are going to miss. And again, okay, so context-free grammars, they just about what we need to account, but there are some problems. They are good enough for us to start working on this problem. Again, tree banks. Without the tree banks, I cannot keep statistics. I cannot keep numbers about it. But tree banks for the parsing is something a little bit different, something a little bit more valuable. Okay, and we are going to use it just for getting the data. Statistic also. We are going to use these tree banks to come up with the proper grammar for the language. Okay, that's what we are going to do. Okay, so somebody has to sit down and parse all the trees and mark them one by one. Usually this is what they do. They run some kind of a parser first. That parser assigns the trees to those sentences, and that person chooses the correct one or just modifies them with the correct additions or deletions. Okay, that's what we do with the tree banks while we are creating them. Okay, this is one example. Wall Street Journal data set. Okay, so what is the sentence? Can you read the sentence?
We would have to
wait until we have collected.
on those assets.
We would have to wait until we have collected on those assets.
Okay. There is a he said stuff, right? He said we would have to wait until we have collected on those assets. He said. Okay, so this is a parse tree sentence, okay, it has this quotation marks in it. Noun phrase, verb phrase. This is the noun phrase. This is the verb phrase. How about this one? Noun phrase, subject he. Noun phrase, verb phrase said. He said. Okay, so it has these two parts, quotation and after that. So here I am trying to say this is this. They usually sit on these kind of sentences. They start with the small constituencies. Okay, when they mark the noun phrase and the verb phrases later, they combine them together. When they combine them together under some rule, that rule is added to our rule of grammar of English. Okay, so while they are marking it, they are actually inventing new rules for the language too. Okay, that's why I said that our tree banks are more valuable than than just having some kind of a statistical data source for us. Okay. Simply take the local rules that make up the subtrees in the trees in the collection, and you have a grammar. It's not complete. You may have other rules that you are missing, but if your data set is a large data set, then you can say that you have most of the rules for this language. Those are the tree bank grammars. And for the tree bank grammars, for example, this pen tree bank, there are more than 4,500 different rules for the VPs, word phrases, because they don't want to use recursion. Because recursion, people are not very good with recursion. Okay, they cannot draw the recursive trees by looking at the sentences. Instead, they say that, okay, after this verb, okay, there could be a one propositional phrase or two or three or four. After four, I think they stop because it doesn't make much sense. People don't use that kind of very long propositional phrases. Okay. So they are not, those grammars are not as nice as our grammars that we have written in a few.
Tree banks are like pre-generated trees that cover a lot of daily life structures, right?
Say that again.
Like pre-generated trees that cover the most of daily life sentences.
Well, I mean, you mean without looking at the data itself?
I mean, without generating the tree, we take the data and we try to fit it in the tree. Does it fit? No. If it doesn't, we like instead of parsing it ourselves.
Humans don't do that. That would be too much work. No, they write a very simple parser. They say that for this sentence I parse it this way. It's okay. It's okay. Then they pass. Otherwise, they made a change. Okay. Okay. Did I answer your question? Then I didn't understand your question then.
Maybe I didn't understand. So, what is exactly the tree bank? Like, is it a trees that are pre-generated that we can just fit
This is
things
this.
in?
Given a sentence, it gives this tree. This is a tree, right? It says sentence.
Okay, I know the tree. So, is it like an algorithm that we give a sentence and gives us a tree, or is it something that fits trees in it?
It's a pair of two things. On the left side you have your sentence. On the right side you have your tree corresponding to that sentence. That's called a tree bank. It is no different than part of speech banks. Okay, data set. For the part of speech data set, on the left you have the sentence. On the right you have the assigned tags.
Okay. So it is not the same as CFG, right?
It's well, you are applying your CFG rules to those sentences and you are coming back with these trees. I have these kind of sentences. I go for this one, it is as, noun phrase, verb phrase, pronoun I, verb, go.
Yes. This is like normal CFG, context free grammar.
Well, yeah, sure. I mean, but isn't this a context-free grammar? Isn't this context-free grammar? Yeah.
Yes, exactly. So I was asking, like, is tree bank a subset of like? I didn't get the idea.
Tree bank is the application of this context-free grammar to some data.
Okay.
Since there might be ambiguities, okay, in those trees, application of this context-free grammar to that data might produce ambiguities. It is the task of the human annotator to eliminate those ambiguities and say that, okay, this is the one, this is the one, or these two are possible. Okay. Okay, so again, let's go back to this head concept. Okay, in trees we like to define these heads. Their uses will be clearer in a few minutes, maybe. Heads in the trees. Finding trees in tree banks is a task, and that's not an ambiguous task actually. And all you do is this. Okay, let's look at this one. Workers dumped sacks into a bin. Good. So we say that for a sentence, the head of the sentence comes from the verb phrase. Verb phrase says that head of the verb phrase comes from the verb side. Okay? So dumped is the head of this verb phrase, and sentence has this head. But for this propositional phrase, the rule says that into has to be this proposition has to be the head. Okay, for this noun phrase, okay, noun has to be the head. So each constituency, each non-terminal has a head defined, and at the top, after we came up with this parse tree, at the top we will have the head of the sentence. Okay. So again, we are going to use this head definition later when we look at the dependency grammars. Okay? And the other thing is important. Head is not just for the sentence only. It is for the sentences, verb phrases, proposition phrases, etc. Okay, so head finding is as I said before, it's just an algorithm. Just run this algorithm. Just do it. For example, this one. For this noun phrase, the head is flights. It's because for this nominal, see this nominal noun. Noun is the head of this nominal. Nominal propositional phrase, it is this one, etc. So this is a simple set of rules. Again, the tree bank uses, we talked about this. Head finding and tree bank itself is useful for us. And now let's talk about this dependency grammars. Unfortunately for Turkish, this context-free grammar thing doesn't work very well. Okay, what did I say about the Turkish? We said that Turkish is a subject, object, verb language, but we don't obey that rule much. Okay, I say ben okula geldim, geldim ben okula ben geldim, etc. I mean, we use all of those, and the thing is that they all each have a different meaning, right? So how am I gonna parse this? Okay, it is noun phrase, verb phrase, noun phrase, etc. So that it's all complicated, and for Turkish, well, it helps a little, but it is not as useful as context-free grammar application to English or French or whatever. Okay, so for these kind of languages, okay, there is another loose way of parsing sentences. It's called dependency grammar. With the dependency grammar, yeah, you have a parse tree, but it is not as strict as the context-free grammar trees. Okay, so this is what we are going to do. We are going to explain the relationship between the words. Okay, that's where the head comes from actually. So, and we are going to take a pair of the word inside the sentence we are going to say that the relationship between these two words are this, okay? And we don't have to say the relationship for all the word pairs, but only one word pair as long as all the words are explained. Here is one small subset of the relationships defined for some word pairs, okay? Nominal subject, okay? This word is the nominal subject of this verb, okay? Clausal subject. This word is the clausal subject of this verb, and etc. Let me show you one example. They hid the letter. They hid the letter on the shelf. Okay. They hid the letter on the shelf. Hid and they are dependent on each other. Hid is the head word of this sentence. This is the head, this is the verb, right? They is the nominal subject of hid. Letter is the direct object of hid. The is the determiner of letter. Okay. There is an on relationship between shelf and the letter, and there is the determiner of the shelf. Okay. So this is very different from, again, context-free grammars, and this tree does not depend on the word order. Okay. This tree does not depend on the word order. I mean, it doesn't matter if I say ben okula geldim, ben okula ben geldim. It's going to produce the same. It's going to produce the same dependency parse tree, because geldim will be at the top of the tree all the time because that's the head. Nominal subject will be ben, or maybe it is hidden here a little bit. Okay, and then direct object is okula, etc. So doesn't matter how you say all those words, this dependency parser will produce almost the same thing for different. So these kind of languages are word order free languages, okay, fluid languages, akışkan diller languages, and Turkish is one of them, because in Turkish most of the complications come from the morphology, within the words. After the morphology, okay, the rest of this is kind of easier compared to English. In English, you don't have much morphology going on with the verbs and the nouns, not much. But many things are going on with the grammar itself, with the word order itself. Okay, that's why context-free grammars fit the needs of languages like English better than the Turkish. For the Turkish, dependency parsing is better. Okay, is better. Since this course is about natural language processing, we are going to look at both of them. Okay. Okay, so dependency approach has a number of advantages. Okay, deal with the free word order languages, quite fluid. Okay, parsing it much faster than context-free grammars. Okay, and dependency structure often captures the syntactic relationships needed by later applications such as the translation and question answering, etc. So we don't have to come up with a complete parse tree for a language to do useful stuff. Context-free parse tree, I mean. It's a parse tree, but dependency parse tree usually is the way to go for some languages like Turkish. Okay, and the approaches are this. Usually what we do is, I mean, you are going to see that for the context-free languages, for the context-free grammars, we will have very nice algorithms to produce all the parse trees that can be extracted, including the ambiguous ones. Okay. For the dependency parsing, we are going to run some machine learning stuff. Okay. Are these two related? Okay. Which one is the main word of this sentence? Okay, I'm talking about the verb itself. And which one is the subject, nominal subject? Which one is the object, etc. So we are going to ask these kind of questions to some kind of a machine learning engine like the support vector machine and that kind of stuff. And later we will find those trees and we will try to make sense out of them. Okay, so these are all the things that I like to say about formal grammars, both context-free grammars and dependency grammars. And now for the rest of this class, for the maybe 10 minutes, I will talk about parsing itself. Where is my, yeah, here it is, parsing. Okay. Okay. For the context-free grammars, we will see two types of parsers, bottom-up parser, top-down parser. Ambiguity will definitely be there, okay? And we will see both examples of top-down and bottom-up parsers. Both of them are based on dynamic programming. Again, we are going to fill in some tables, and we are going to show you parse trees, all possible parse trees for a given sentence. Okay. So parsing is this. Parsing is assigning a tree or trees to given input string. Book that flight from Ankara. Book that flight from Ankara. It's a sentence in English. And if I parse this sentence, actually there are. Can you translate this to Turkish? Book that flight from Ankara.
Ankara'dan olan uçağı ayırt. Ankara'dan olan uçağı ayırt.
Uçuş.
Uçuş, özür dilerim.
Ankara'dan olan uçuş ayır. Or that's one meaning. Ankara'dan olan uçuş ayır. Or
Ankara'dan uçuş ayır.
Don't do it in Istanbul. You do it in Ankara, right? Okay. So Ankara. So is it the same thing? Ankara'dan uçuş ayır. Ankara'dan olan uçuş ayır. I think we are saying that with a different Ankara'dan ayır. So our stress is in a different position. Ankara'dan uçuşu Ankara'dan ayır is one of them. Ankara'dan olan uçuş ayır is another one. Okay, so it is two different sentences, but it has two different meanings. So when I parse this sentence, this parsers should give me two different trees. Okay, and it should reflect it. So the flight from Ankara, it could be a noun phrase, or okay. So now verb phrase and noun phrase, or verb phrase, noun phrase, and propositional phrase. So the from Ankara is part of this verb phrase, could be. So that's the parsing thing. Okay. Proper parsing means that extracting all the possible parse trees. We are not saying that we should disambiguate which one I like to mean. Okay. No, parsing cannot do that. Parsing only tells you this is one way of parsing stuff and this is another way of parsing stuff. Okay. So disambiguation is something else. So we are going to pass all the parse trees to the one level up, to the maybe semantic analysis and that kind of stuff. Okay, but it doesn't actually mean that the student can select the correct tree from them. Okay, so again, parsing is going to be search. We did lots of search, and sometimes we did it very efficiently, like in the case of edit distance, or in the case of part of speech assignments. And we are going to do the same thing, another type of search now, to find to assign the correct parse trees. And these will be the assumptions. Okay, we already have the words already in some buffer. What does that mean? We don't start parsing before seeing the whole sentence. Humans don't work that way. Okay, when we talk, we we say the words in groups, but we don't say the whole sentence before we stop. Okay, maybe I say the noun phrase part first and wait a little bit to give you the verb later, but I don't say the whole sentence for you to understand before you start processing. Okay, so but this one say that you get all the words in some buffer and start parsing later. Okay, so we never argue that we are going to parse it like the humans. Humans work differently. Okay, it's like the you cannot compile a program without seeing the whole program. You have to see the whole program to compile it. My input is not part of speech tagged. There might be lots of ambiguity. So word take could be a noun, or could be a verb, or could be an adjective, and etc. We don't know. Morphological analysis we will ignore. Okay, well, very bad news for Turkish. Okay, because maybe for English, by ignoring the morphological analysis, you can go from A to B, but in Turkish, no, you will stay at A. You are not going anywhere. But this is how it works for the English, actually. Okay, and all the words are noun. If I don't know the words, this will not work. Okay, and some of them are very strong assumptions. Well, they may not be compatible with the real world cases, but this is the way it is. And maybe we can solve some of these problems later. Okay, first, let's do the top-down search. Again, this is what we are going to do. We will start with an S. I have a sentence, for example, book that flight from Ankara, and I will start from the top, from the S. I will start expanding my sentence using the rules, and I'm going to see if I am matching all the words with the current tree that I have. This is called top-down search, and this is what we are going to do here. Okay. So a sentence, again, book that flight. That's what we are going to do. A sentence could be a noun phrase, verb phrase, or auxiliary verb phrase, noun phrase, or verb phrase. Okay. And then this noun phrase, verb phrase can go into okay, noun phrase, determiner, nominal. This noun phrase just proper noun, sorry. Or in this case, it could be, this noun phrase would be determiner, nominal, or this noun phrase could be, you understand what I'm saying, right? At each step, there are many options that I can go. So this tree, this is a search tree, right? This tree, whose elements are trees, is getting larger and larger and larger. So I am trying to reach a case like this. Book that flight. You see this? Book that flight. So I am going to say at the end, okay, here is my parse tree. This one explains my input sentence, book that flight. Am I done? When I do this, am I done?
No.
No, why not? Because
You have another tree.
I might have other trees, right? I might have ambiguities. I might have other trees. Okay, so that's the rule. So if you do it, the search like this stupid way, that's what you need to do. Top down parsing. If I do the other stupid way of doing things, bottom up parsing, okay. This time I start from the sentence. I start adding non-terminals on top of the words, and here it is. Book that flight. Would could be a noun or verb or adjective, but let's say I'm going to choose the correct ones. Verb, determiner, noun. Okay, nominal noun flight, and these came together with a noun phrase, and these two came with a verb phrase, and verb phrase is directly connected to a sentence. Now I parsed it. Okay, of course I had chosen the correct path all the time. Again, book could have been an adjective, a noun. Would could have been another stuff. Okay, flight that didn't have to be a noun and nominal, etc. So bottom-up search works this way. Again, when I obtain this as, does that mean that I am done? No, because there could be other ways of parsing this sentence. That's what we are going to do. So top-down and bottom-up, both of them, if you are not doing it a smart way, if you are not smart, then you are stupid. The examples that I showed you are stupid examples of it. But there are some advantages of top-down and bottom-up. Top-down is nice because at every step, you are only looking at grammatically correct alternatives of doing stuff. But you are looking at a very, very large space. Bottom-up, it is not that way. You are only looking at the trees that are compatible with the current input, but those trees may not come together in a single sentence. Okay. So that's basically it. So next, I think I'm going to stop at this point. Next lecture, I am going to show you a parse tree method, okay, parsing method. CKY algorithm is going to fill in these kind of tables, and at the end we are going to say that book the flight to Houston. Okay, book the flight to Houston. As you see, I have one sentence here and one sentence there. The important thing is that I should have one sentence here. So what is this? Book the flight is a sentence, right? But I don't like it. Why? Because it ignores these two. But this one makes it. Let's continue doing this. Let me show you. Okay. So it has three meanings actually. Book the flight to Houston. The flight to Houston, that's one case. The other one is this flight to Houston. The other one is book the flight through Houston. That's the second one. How about the third one? Where is the third one coming from? What is the third meaning for this sentence? Okay. That will be the cliffhanger for you for next week. So you will have to wait until next week to see what is this S3 is, what this S3 is. Okay? Book the flight to Houston. There's the third one. Okay. That's it for this week. I will see you next week if there are no questions. No questions?